Okay, the next speaker in the session is Marianne Cowherd from UC Berkeley. She's studying ecosystem sciences with Manuela Giotto. She's done 2 practicums at PNNL and Lawrence Berkeley National Lab. Let's welcome Marianne.
I'll open in front of that. Thanks, everyone. My talk is titled Climate Change Impacts on Seasonal Snow Measurements, and I'll get to every word in that title and talk to you about the 2 projects I did out of my 2 practicums. And I am lucky enough to not have to introduce the liquid or solid that I'm talking about, unlike some of the other people who are doing chemistry, because I'm talking about snow, which is also water. I am going to introduce snow as a supply, storage, and information source, because sometimes people think of it as just a fun, fluffy thing and not as an incredibly valuable resource. Snow differentiates itself from some of the other phases of precipitation, like hail, by not being really annoying, and also from water by providing more than just a water supply. It also provides its own storage and information, but it acts kind of like a version of the marshmallow test that you give to children to see if they're patient or not, except instead of having to wait and be hungry and want the marshmallow until you get your second marshmallow, you get to play the marshmallow game without even wanting the first one. So that's snow falling in the winter, freezing itself, waiting, and then melting in the summer, running off into all of the world's most important agricultural regions and many of the largest population centers. In graph form and not picture of cute kid form, we see this happening with snowfall happening preferentially in the winter when it's colder, and then running off as stream flow when it's warm and hot outside and we want to grow crops. However, this happens usually far away from where we're actually using it, so in the mountains and in northern regions. So we have to make decisions about how to manage our water before we receive it in the summer. This is a bonus. We have many months to make on-the-ground snow measurements as we're waiting for it to melt off. But it's also difficult because it's difficult to measure with a satellite, and we're often limited to using ground-based measurements. In the case of the Western United States, which has one of the best snowpack measurement networks in the entire world, we still make these from manual measurements done by individual people who walk out into the woods and stick big sticks into the ground, and from in-ground scales called snow pillows that were often installed by people walking out on mules in the 80s. And this is still how we install and maintain snow pillow stations to this day. There's not actually really a better way to do it. Sometimes we get helicopters, but it's usually actually with mules. So this is our state-of-the-art snow measurement platform, and it's also the most useful because we have a really long time record for measuring snow, often going back into the 80s. And we would expect in theory that every time you get more measurements, you get your time series longer, you get a better statistical ability to estimate things like the mean and the standard deviation. But hold on to that thought for a little bit, because it's not always so simple, because we want to know where we're going into the future, and we especially want to know where we're going in the future as we get more carbon dioxide in the atmosphere and a warmer atmosphere. Which brings me to my 2 practicum topics. The first one on the changes in atmospheric drivers of Western US snow drought records, and the second one on measurement systems and how we are able to use our in-ground snow pillows. And this is driven by our knowledge of how climate is changing the hydroclimate system in snowmelt hydrology, river flow, and all sorts of other topics, including potential increases in snow deluges in addition to lack of snow, and further questions about water management as we go into a more uncertain future. In my first practicum, I went to Pacific Northwest National Lab, where I got to work on E3SM and on CompuMcNodeface, the best named supercomputer. And we looked at ensembles of climate models run by in the US and around the world, and looked at trends in statistical snow droughts. This is similar to a drought that you might get in like a normal warning from a government agency, but specifically focused on snow, not other phases. And what we found is that in 2 different middle-of-the-road and high fossil fuel development future climate scenarios, we saw shifts in the distribution of the snow drought metric that we focus on toward the more negative, which is less snow. We saw different rates of shift in the different climate scenarios and in different regions of the world, but the trend was still very consistent and was increasing compared to our baseline period from 1850 to the present, where the statistics were approximately stationary. This was a pretty expected result. We thought as it gets warmer, we'll probably have more snow drought, but we really want to know why, and we want to know what the spatial variability is on the scales that we're making water decisions, not just on the very coarse scale that we're running native resolution climate models at. So we had to take a step back and think about the things that lead us to get snow, which is generally water and cold. We can have a low water year, which we call a dry snow drought, a warm year, which we call a warm snow drought, and you'll never guess this, but if you have both, we call it a warm and dry snow drought. Previous work looking at past records have told us that warm snow drought is the least frequent and least severe of the 3 snow drought types. That we get very bad years when we don't have enough precipitation, but when it's just a little bit too warm, it's usually not that bad for snow water resources. But when we decided to start applying this to future projections of future years, the first thing we had to do is we had to move to a higher resolution, higher spatial resolution climate simulation, because we weren't really able to resolve very many warm snow droughts at low resolution. So these results come from a different set of climate simulations, which we've run dynamical downscaling on to have higher resolution. And we found that when we looked at the past, this tended to be true. There were not very many warm snow droughts. That's the dark red color. But when we moved into the future, almost all of our dry-only snow droughts went away, which again we expected because the world's warmer. But instead of being completely replaced by warm and dry snow droughts, a larger proportion of them were warm only. These did tend to be a little bit less severe, but it led to a situation where if you have a warm snow drought, this means you have a normal or high amount of precipitation. So if you're tracking droughts by just looking at your total precipitation, you might see a year like this and think everything is actually totally fine. And if you just care about how much water you're getting out of the sky, you'd be right. But if you care about getting it at the time that you want it and with a lot of heads up time to be able to make decisions about groundwater pumping or other water resources, this is actually a pretty bad situation where you could end up with practical droughts even if there's technically enough water in your region, but it might flow out to the summer or out to the ocean or run off in the winter when your plants aren't growing anyway. There's also a lot of spread in these types of projections that's mainly driven by a disagreement in different climate models over local precipitation trends. Because warmer air tends to hold more moisture, and because storm tracks tend to change in future climate models in ways that don't necessarily agree with each other, we weren't able to get a consistent direction of the change in total precipitation. So about half of the models in our model ensemble showed a decrease in precipitation, and the other half showed an increase in the Sierra Nevada, and this isn't something that's been resolved in the climate modeling community sufficiently. The third problem that interesting thing that we ended up with is that when we look at the response of snow to temperature change, and in this graph we're showing for every degree of temperature change in a global climate simulation, what's the local response of snowpack, where blue is positive and red is negative. We have a very specific spatial pattern emerge, which is that most regions in California see a decrease in snow with increases in temperature, but there are some regions that see an increase in snow. So for every degree of global warming throughout the range that we see through the end of the century, the top parts of the Sierra Nevada ridge see an increase in snowpack because the warmer, moister air precipitates more, and there's still room to move in the temperature range. We see this again when we look at just by elevation. This is concentrated in the higher elevation regions. So some of these regions, they might have changes in snow drought statistics, but there might just be a spatial shift in where the snow's going. So we also need to know this when we're thinking about how we might use measurements that are made at different places in these basins. To put this a different way, we wanted to know where snow will increase or decrease when the temperature increases, and identify places where this is a positive signal or where it's more moisture dominated, and where it's freezing dominated or a negative signal. To do this, we ran spatially explicit models looking for places where the change in snowpack per change of temperature was positive, and found that in high elevation regions that tended to be on the leeward side of mountain ranges, this was more common. When we switched it to look at the places that were freezing dominated, we found that locations that already have a lot of precipitation but tend to be a little bit warmer, like in the Pacific Northwest and on the windward side of mountain ranges, this was the case. So in this set of projects, we found trade-offs between water availability and freezing when it comes to future Western US snowpack trends. But this doesn't necessarily, and then I decided to do a second practicum because I met someone at Berkeley Lab at a conference, and we had a lot of shared interests in looking at climate change and predictability. This person's name is Dan Feldman, and so I emailed Dan Feldman and I said, hey, can I do a summer practicum with you? And he emailed me back and said no, but then I emailed Dan Feldman again and he said yes. So then I did another practicum. And in this one, we were looking at this question I've been talking about, which is where our snowpack is moving and where we're putting our measurements. So we're looking at projected futures where our snowpack is moving up, our center of mass is moving up, but the snow depth at the top might be also increasing. But our measurement stations are staying in the same place. So we were talking about this and we thought, okay, first, no one's really quantified how much of a problem this is. And it turns out that quantifying how much of a problem it is really difficult because it's a different type of problem in every single management basin, and there's no set size or agency for a management basin. So we decided to do this on a more theoretical basis, which is first we started tracking all of the locations that were measuring snow in the Western US. This is about 900 stations, each with its own mule team. What do we expect the snowpack record to look like in the future? What do we think we'll know about snow in the future? This is the best one in Colorado. I picked it because I think it's the best. And what we're noticing here is there's a peak for every year. That's the peak of winter, most snow. And then you can see like a moderate downward trend, but it's not really that visible. And then we picked the worst one. It's named Calamity, not because it's the worst, but because that's the region. But it is a calamity. If you take a look at this one, we also see the big peaks. And then at the end, we see kind of nothing. And in theory, that should be fine, except when we look at the basin that Calamity is in. This is all of the other points in this basin that aren't being measured. We see there's sort of the same general downward trend, but toward the end of the century, there are some years where we're not getting any information at all from the Calamity station, and we're getting a lot of variability in the rest of the basin. So kind of at the end, by the end of the century, there's not really a lot of value to having the station. And this is the type of situation we're starting to see ourselves in more, where there's actually something meaningful going on. There's interannual variability in water storage and supply, but we're not really going to be able to see it very clearly. And this is kind of difficult to confront because we're used to having increases in technology, increases in length of time series, and to be able to make better predictions in the future. We're finding situations where we're actually making worse ones. And this is another view of that type of challenge. We're having, this is sort of a typical basin in Colorado. We have some number of sparse observations and we're trying to predict the entire snowpack field. And when we start quantifying this type of challenge, generally how much worse are we going to be at making this type of prediction? We see a decline. This is consistent over an ensemble of 9 different climate simulations that use have independent snow and precipitation fields. We would like there to be a static correlation. This is assuming the exact same measurement and prediction setup that we have right now, but we see that it's going down. So for the rest of my practicum, we tried to come up with different techniques for addressing this decline toward the end of the century. So a climate resilient way to make distributed snowpack distributions. We tested a lot of different setups, and we were motivated by the thought that one of the things that we're getting wrong in our current setup is that we're assuming a lot of the snowpack relationships between measured and unmeasured locations are linear. So we started working on some nonlinear modeling. And our first try was to try a random forest model, and it worked really badly. Our other linear cases here have something else going on, which I'll get to in a second. So just addressing the nonlinearity, which would have been the easiest solution. It's pretty easy to do nonlinear modeling, didn't work very well. And so next we thought, okay, well, this is really like a 2D spatial correlation problem, so we should add in some 2-dimensional components to our algorithm. We did that. That actually worked really well. We could have just stopped here. We also decided, okay, not everybody's going to want to use any different algorithm than they're currently using. It could also be legally mandatory. So we should also try to give it some more forcing data. So these are relatively generally available precipitation and temperature fields that are available, not necessarily in real time, but pretty easy to acquire, but a lot of water management systems don't currently use them. And we found that it was necessary to have a nonlinear component and also some two-dimensional component, but it didn't actually matter which one of these two, so you could pick any and you would end up in this very high performance region. So to conclude, we've found that we should very carefully use certain types of machine learning algorithms, and that could make current measurements climate resilient, but you could also use two-dimensional precipitation and temperature fields. And that lack of actionable information about snowpack is a parallel challenge to lack of water. You can have actual water shortage or an information shortage, and they can cause similar problems when it comes to water management. And last, we were bringing up ideas in how climate change is threatening our ability to understand the effects of the change by degrading the ability of measurements to give us actionable information about quantities like water that we'd like to manage. And I'd like to finish up by giving some acknowledgements to my practicum supervisors, collaborators, funding sources. I think all of these are somewhat DOE related, especially the SAIL project, which is the field project that I did most of my snow pit digging with in grad school. This was actually really fun, even though it may not look like it. And to everybody in my cohort and the CSGF that I've gotten to spend so many years with. So I think I have time for questions. Thanks.